Programming a computer usually means moving abstract data around on a screen. But in embedded systems, software has to reach out and manipulate the physical world. This University Embedded Systems exam asks us to write a C program that monitors a door sensor and sounds a buzzer when that door opens. The sensor is wired to pin P1.1. The buzzer, connected to P1.7, requires a continuous square wave to activate. Fulfilling these requirements requires a C program that bypasses the usual abstractions of a desktop operating system to address these specific pins directly. Our target environment is the 8051 microcontroller. It operates under strict, finite physical constraints that dictate exactly how memory and processing cycles are allocated. Writing embedded C for this architecture is about explicitly mapping software variables to physical pins and manipulating real-world electrical states in real time. A modern desktop processor measures its RAM in gigabytes. The 8051 measures its internal data memory in bytes, 128 bytes to be exact. Furthermore, the 8051 is strictly an 8-bit architecture. Its data paths process information exactly 8 bits at a time. This creates an immediate problem with standard programming habits. On a PC, a developer will typically declare an integer, or int, for a simple loop counter without a second thought. But the standard int data type requires 16 bits, or 2 full bytes of memory. Forcing an 8-bit microcontroller to process 16-bit variables burns through extremely limited RAM and slows down execution. To avoid this waste, assembly language requires developers to explicitly manipulate 8-bit hardware registers, like R2 seen here, keeping operations lean and fast. To retain the readability of C without sacrificing that raw efficiency, we have to adopt data types that align perfectly with the physical hardware. Successful 8051 programming requires memory as a scarce physical resource and using data types as strict allocation tools to manage it. This table outlines the specialized data types provided by 8051 embedded C to solve this constraint. The unsigned char must become the default replacement for standard integers. It occupies one 8-bit byte and holds values from 0 to 255, which covers the majority of basic loops and counters. Internal counters are useful, but the door sensor prompt requires us to monitor the voltage state of a specific physical pin and output a frequency on another. For this, we look to the SFR data type, enabling C code to directly address 8-bit hardware registers in RAM. Even more precise is the S-bit, or single-bit data type, granting bit-addressable control over individual I/O pins. To set up the exam problem, we declare S-bit door sensor equals P1/1 and S-bit buzzer equals P1/7. Declaring S-bit variables is the crucial step. It bridges abstract software names directly to concrete electrical connection points on the chip. With our I/O pins mapped, we can construct the execution logic. Desktop applications open, run, and close. An embedded program operates continuously, keeping the hardware awake to constantly read its environment. This requires a permanent repetition structure, illustrated here by the while loop flowchart. We encapsulate the entire main program inside a while-one loop, creating an infinite, unbreakable cycle of execution. Inside this infinite loop, the system repeatedly checks the physical voltage state of the door sensor. We use an if selection structure to read that voltage state. If the door opens, the voltage changes, the condition becomes true, and the logic flows into the trigger commands. In embedded systems, while and if statements operate as active, high-speed physical polling mechanisms monitoring the real world. The final requirement is triggering the buzzer. The exam specifies generating a square wave of a few hundred hertz. Creating a square wave means rapidly toggling the buzzer pin between a high state of 1 and a low state of 0. This introduces a timing conflict. The microcontroller executes instructions in microseconds. Toggling the pins sequentially cycles the state too rapidly to produce any human audible sound. We have to force the processor to stall between toggling the pin high and low, artificially stretching the waveform out. The primary tool for creating this time delay is an empty for loop. We deliberately use an unsigned int. An 8-bit char counts to 255 too fast. A 16-bit unsigned hint counts into the tens of thousands, providing enough processor cycles for a noticeable delay. A loop that does nothing is usually bad code. In hardware programming, it's an essential tool for aligning machine speed with human perceptual time. There is a critical caveat to this technique. A software for loop does not represent absolute time. The exact duration of the delay relies entirely on the physical hardware driving the microcontroller. Every instruction executed by the 8051 is paced by a system clock, driven by a physical crystal oscillator mounted on the board. The frequency of that crystal dictates the exact duration of a single machine cycle. If you swap the crystal for a faster one, the for loop finishes sooner, and the pitch of the buzzer changes. Embedded software timing is inextricably bound to the physical clock physics of the board it runs on. We assemble our complete C program, declaring single-bit variables, initiating the infinite polling loop, evaluating the sensor condition, and executing toggled delays. In real-time operation, the system initializes and immediately enters its continuous cycle. When the physical door opens, a high voltage hits pin 1.1, and the if statement evaluates true. Pin 1.7 toggles high, stalls via the hardware-dependent for loop, then toggles low, producing the required square wave. This specific software architecture perfectly satisfies the physical requirements defined by the exam prompt. These techniques scale well beyond simple switches and speakers. Moving forward in the same exam, Question 3 introduces much more complex peripherals, driving an LCD screen, reading pressure data via an analog-to-digital converter, and writing to an EEPROM over an I2C protocol. Interfacing with these advanced components requires the exact same foundational tactics: strict data typing, git-level addressing, and precise loop control. Developing this proficiency transforms the C programming language from a simple data processing tool into a highly precise instrument for physical hardware management.